Okay, welcome to the first session after lunch.
Cool.
And we have Morten Kromberg here talking about notation for parallel sorts, representing Dyalog. Dyalog is providing the world with one of the leading implementers of APL, I guess I can say.
Thank you.
And,
yes.
The floor is yours.
Thank you very much. Yeah, so I mean, in Brad's talk right at the beginning, there was somebody asked the question. I don't know if it was Brad himself. You know, is there anything going on with array notation and so on? So here I am representing a 50-year-old technology, and of course my answer is yes. There's a lot going on. I'm going to start with some history, brief introduction to APL as it was back in the 60s. And then talk about various things that were added to the language through the decades, including very recent work that we're doing to add asynchronous programming and so on. And my point is going to be that this is still very much a relevant notation that you could perhaps be using. I mean, you are all experts in making this run fast, I think. There have been a few presentations like Brad's on the importance of the notation. But most of what we've heard has been about, you know, detecting loops and unrolling them and so on. Many thanks to the program committee for allowing me to come here. It's been very good for me to come out of the talking to actuaries and physicists and so on who are using this technology and get some inspiration from people who are really looking at modern hardware and how to make stuff run fast. And several people should be mentioned up front. Some of them are here today. Aaron's going to be speaking after me. Bernecki had a paper presented last year, I mean. But I thank them now because I'll forget at the end and run out of time. Right, so the title of my talk, Notation for Parallel Thought, of course, is stolen from the title of Kenneth Iverson's Turing Award lecture in 1979. And as you can see, it's really about notation. He talks about, he's quoting great minds who came long before us, talking about the importance of relieving the human brain of unnecessary work, increasing the mental power of the race. Maybe that's a difficult word to use these days. But anyway, this is what was inspiring Ken Iverson when he designed the language. And I'm going to try and demonstrate how that's as relevant today as the hardware has changed. In fact, maybe more relevant than it was back in the 1960s. A few words about Dyalog and then myself. So Dyalog is an APL vendor. We're based in the UK. We have people all over the world. We've been working, we call ourselves the new kid on the block. We've only been around for 35 of the 50 years that APL has been on the market. IBM had the first APL interpreter up and running in 1966. Our revenues are sort of pretty much split across the world, half in Europe, half in the rest of the world, most of that coming from the United States. I don't know if you've heard of this thing called Microsoft Windows. I assume researchers are mostly using Linux and Mac, but most of our revenue still comes from Microsoft Windows and IBM's Unix for running their mid-frames, if you like, the AIX system. But we are expecting a big shift to Linux to happen in the very near future, driven by parallelism, cloud computing, and so on, is really warming the fires up under Linux. Most of our revenue comes from people who've been using APL in the financial sector to do portfolio management, that kind of applications, for decades. But we do have a number of people using it in manufacturing. We have healthcare applications. That's quite interesting. A lot of the new applications that people are working on are things to do with genome analysis and that kind of thing. It's, we've been around for 35 years. I'm happy to say it's a slowly growing niche market for us. That may not be true for all of the APL vendors. You probably think of those of you who have heard of APL at all think of it as some kind of dinosaur that existed in the 70s or 80s. But remember that some of the dinosaurs evolved to become birds, I think. And I'm here to enlist your help in making that happen, perhaps. So we're making money, we're funding research, and in fact, I would say that we are doing as much R&D today as the major vendors, IBM and Sharp and so on, were doing back in the first golden age of APL in the 1980s. And the emphasis now on arrays and functional programming and parallel programming makes us feel that there's actually an opportunity for us to engineer the second coming of APL. I was born in the same year that Ken Iverson published his original book. It's important to remember Iverson's goal with all of this was not really to make a language for programming computers. He was concerned with teaching mathematics. And APL was used on, it wasn't whiteboards back then, it was real blackboards for about 4 years before Iverson moved from Harvard to IBM and was involved in the project that led to the first APL interpreter. So the design of the APL notation is not so much aimed as making it easy to compile or interpret as to make it easy for humans to communicate with each other about mathematics and data structures. So I was born the same year as the book. I've been an APL consultant. I'm a one-trick pony, if you like. I've been doing APL since 1979 and still having a lot of fun with that. I had a varied but brief academic career and got into writing real applications for people. And now I've been at Dyalog for the past 11 years and just handed over the responsibility for really managing the development team and so on to people who are better than that. And I'm now out there talking to you guys and listening to our own users to understand what they need next. So here's the problem that Ken Iverson set out to solve. He learned mathematics fairly late in life, he was born on a farm, and he went, after high school he went back to work on the farm, but then fortunately he was drafted by the army, and he met some people there who made him study a little bit of math, and then said he had to go and go to university after the army. So he came to this very late, and maybe that's why he had a little bit of a different perspective on what he learned there. He was already probably older than many of his fellow students when he was learning mathematics. And he looked at all these things, and they annoyed him. There's a wide variety of syntactical forms, very strange and inconsistent precedence rules, which might depend on the context that you're operating in, whether there's been some trigonometry going on might change the order of evaluation and so on. And at Harvard, he worked with Leontief on the input-output model, which involved a lot of matrix work. So he got into matrix algebra, and there the precedence rules and so on are even more inconsistent. So he thought about this for a while, and he organized it all in his mind. And he came up with the idea that you could just write a times b, e to the power x, x divided by y, the base b logarithm of a to the power reciprocal n is the root. Matrix multiplication is the inner product with plus and times. Fgx, and this in fact is the precedence rule that he elected for the entire language. He said, this is the basic common form of mathematics. A function applies to the result of evaluating what is to its right. And then if you have functions which take an argument on the left, you just fit that into the structure. So there are your sigmas and your pi's. And the last one is a little bit more involved, but there's not more going on there really than you have in the original mathematical expression. When you're reading APL, some people, because each function takes everything on its right as the argument, as the right argument, the result of evaluating everything to its right, people say that APL executes from right to left. Most of the time that doesn't mean you'll read it from right to left. You would, if you take that expression we had at the bottom of the previous slide, ideally read that as 2 times a divided into minus b plus or minus the square root of b squared minus 4ac. So with a little bit of experience with APL, when you see something like that, you would read it from left to right, and if you find that you lose the ability to do that, you should probably break it up into sub-expressions, as you would in any programming language. Okay, so the language that he came up with for this is extremely simple. This is the entire description of the syntax of APL. There's very, very few moving parts. You can have an array, and numeric arrays can be constructed simply by juxtaposing numbers. You just type in numbers with spaces between them. That gives you a vector. You can have a function with an argument on the right. That's called monadic function. Unfortunately, other people have come along and stolen the word monad later, but Ken was there first. You can have a function which takes a left argument and a right argument. We call that dyadic. You might call it infix. Then you have things called operators, like the slash here. So the slash takes a function on the left and returns a derived function. So that's plus reduce, which is a term which I think most of you are familiar with, but this, I think, is the original notation for plus reduce in APL. So that's a times reduction. That's the multiplication reduce. And then actually a little bit later than the 60s, I think this came along in the 70s, a left argument to reduction specifying a window size. So the 2 plus reduction is a plus reduction for consecutive windows into the array. And then you have dyadic operators, in this case the dot, where you have a plus on the left and a times on the right is the standard dot product, vector product. And then indexing, which is the same as in most languages except that you can index with an array. So we're indexing here with a 4-element integer vector and getting an array result which has the same shape as the array being used for indexing. Okay, so I mean, we've no reason to spend a lot of time on these. I think they all work the same way. You can have conforming arrays, you can have only one scalar on the one side, and you then get scalar extension. There's a number of functions, but there's not that many. There's about, I guess, 50 functions to learn, and then you've learned all there is to know about APL. It's like chess. You can learn the rules very quickly, and then you can start combining them. So this is scalar extension being applied to a matrix. On the right, we have the 2-3 reshape of the numbers from 1 to 6. So we have an array here that goes 1, 2, 3, 4, 5, 6 in 2 rows and multiply that by 10. And this is the function to produce random numbers. So we're rolling 4 dice there. Okay, so this is, you've all heard of reduction, so I hope I don't, bore too many of you here. This is really about the notation. So you have a matrix. And of course, in APL, everything applies automatically to higher rank arrays. We don't just reduce vectors. So the multiplication reduction of this 2-dimensional array, by default, goes along the rows. So you get the times reduction of each row. You get a 3-element vector out. The display there is slightly misleading. That looks like a column vector, but it's actually just a vector. A reduction always reduces the rank of the argument by 1. So if you have a 2-dimensional array, you do a reduction, you get a 1-dimensional array. You do a reduction of a vector, you get what we call a scalar, but that's not a different data type in APL, it's just a 0-dimensional array. If you use the slash with a little bar going through it, you get the multiplication reduction, going along the leading dimension. And there is a syntax where you can say reduction and then in brackets a number, which then directs APL to do the reduction along a particular array. Scan is the same as reduction, except you're accumulating the results as you go. But the syntax is exactly the same. Outer product, 2 vectors combine all the elements from the left and the right. So if we have 2 elements on the left and 3 on the right, we're going to get a 2x3 matrix back and fill in the numbers. All right. And of course in APL that could be any function, including user-defined function, because user-defined functions have the exact same syntax as all the primitive functions. They can be prefix or infix, and that's it. And many computer scientists would point to that as a weakness of APL, as an inflexibility, but it means that user-defined functions combine with all of the operators in exactly the same way as primitive functions do. So your user-defined functions can act as building blocks in exactly the same way as the primitive functions and operators do. Inner product, so the plus dot times is the dot product, the matrix multiplication. If we look at this number, the second element in the first row, it's produced as the vector product of the first row of the left argument with the second column in the right argument, and it's the F reduction of the map of G to the two vectors that are input, right? But again, Iverson didn't want to make this, this is just a matrix multiplication, but he saw it as a much more general mechanism. So, you could just replace the functions with and equals, for example. And there's a whole bunch of function combinations that are actually quite useful. So this one would say, are there any columns of M2 which are identical to rows of M1? And you get a 2 by 2 matrix back telling you where that's the case. You can do, transitive closure and computations of path lengths and so on if you have destination matrices and so on, using repeated applications of this inner product with and or max and min and so on. Okay, now there's a whole bunch of mixed functions. I'm only going to show you a few of them just to give you a flavor of what they're like. So the scalar functions that we saw before, and the ones that we've been using so far in all of the reductions, are things which have this automatically built-in map. So plus, times, divide, all the regular mathematical functions are what we call scalar functions, and they do this scalar at a time operations. The mixed functions don't, the rule, there are no general rules for them. They are all special cases. So in this case, we have rotate. So here's our matrix. We can do a 2, 0, 1 rotate along the last dimension, which is you can sort of think of it as you can see it spinning around if you imagine it. So this row has been rotated by 2, this one by 0, and this by -1. So the positive numbers are a right shift, and the negative numbers are a left shift. And there's a function with the bar going through the circle horizontally, showing that you're rotating the columns, and there's also a notation to say which dimension you want to do the rotations along, if you want to pick a particular one. Take and drop are very useful. So if you have a matrix, you can either take, in this case, the last 2 rows and the first 2 columns, or you can drop the first row. You don't have to provide you don't have to provide a vector which has the same length as the dimensions. It acts on the leading dimensions and keeps all or drops all of the dimensions that you've left out.
If the vector is too long?
If the vector is too long, you get a length error, I think, or a rank error. I'm not sure which of the errors it prioritizes. Transpose. So transpose, that's an obvious one. You can provide a left argument to transpose, which tells the interpreter in which order it should increase the indices on the various dimensions. So you can reorder the dimensions in any order that you like. If you have repeated indices in the list of dimensions, then it'll increment the indices on both of those dimensions at the same time. And the result of that then is that you can extract diagonals using a transpose with repeated left arguments. So the 1-1 transpose extracts the major diagonal from a matrix. Index of. That's a lookup. So we're looking up the right argument in the left argument. We get an array which has the same shape as the left argument. So 1 is found in the second position. Yes, I apologize. APL, like Julia and Excel and various other things, operates in index origin 1 by default. But you can change, in APL you can decide whether you want 0 or 1. You can set a switch. And everybody agrees that that switch is the most horrible thing almost in the definition of the language, and we're just waiting for an agreement on which value to pick. Some people have suggested 0.5 as a compromise. But at the moment, by default, it's an end user tool, and end users generally are more comfortable with 1. People who've written code in C or assembler or anything where you needed to use a set of bytes to address some region of memory, of course, all know that 0 is the only correct index origin. It's because there are two operations. There's indexing and offsetting, and we've combined them into the same thing, and therefore we have this duality. Anyway, so in the original APL, you could only search a vector left argument, but actually recently it's not fair. These shouldn't appear in these slides, which are really documenting APL as it was in the 1960s. But I thought I'd throw it in here. So we recently extended, this came in J and Sharp APL in the late 80s, that you can search a higher dimensional array. When you search a higher dimensional array, you're searching for items of rank 1 less than the left argument. So because we're searching a 2-dimensional array, we're looking for vectors. Therefore, this is a row lookup. Okay, so here's this is where we were in 1966. There's the scalar functions, there's reduction, scans, outer product. These are all terms that you were familiar with, I think, nearly all of them. They've been there right from the start. And they are sort of parallel in that map is implicit in the scalar functions, and in recent years in our interpreter we have done some work to we decided we were going to be a bit conservative. If the arguments are large double arrays or decimal quad precision arrays, then the interpreter will automatically use multiple threads on these SIMD operations. So there's 4 benchmarks here where I'm comparing the addition of 2 arrays that are only going to run on 1 core and the addition of 2 arrays that are running in parallel. That's why these are called P. They differ in size by 1 item, which just takes the P guys over the edge where the automatic parallelization kicks in. And this is run on my laptop here, which is an i7. And you can see that it's not worth doing on Plus because the memory bandwidth won't really support going parallel. In fact, that test often slows down. You do division, you start to get a little bit. You do logarithm. Now we've got both cores working. It's trying to hyperthread, but it's not really working. And then if we do a GCD between 2 floating point arrays, we actually end up with something where there's enough computation going on in local memory that the full caching, the hyperthreading actually completely kicks in, and I get close to heading towards a 4 times speed up. But these things don't speed up customer applications very much because there's not that many very large arrays in the commercial applications that we have today, unfortunately. So we need to start parallelizing larger units than just the simple array operations. If you'd like to learn more about the stuff we've looked at so far and the stuff that's to come, there's a little website, tryapl.org, which is an interactive APL interpreter, where you can type APL expressions in and have them execute, and then you can hover over the cheat sheet, for example, and see all these definitions of the functions. Okay, so, and then just when I got interested in APL and started using it, there was this terribly exciting period in the 1980s where nested arrays arrived. IBM and various other vendors, there was a race to get this out. So any item of an array, rather than just being a scalar integer or a character, which was what they, before this time, every item of an array had to be the same type. Well, there's only two types in APL, character and number. But you had to have homogeneous arrays of those. So APL2 came along from IBM, and in addition to the automatic mapping, we also got something called pervasion. We got this notation where if you juxtaposed arrays with a space, there's such a sort of a function going on here, it would that would give you a two-element array where the first item is a vector and the second one is a scalar. And then here we have a vector and another two-element vector where the second item is another vector. And you get the mapping at the top level, so 1, 2, 3 times 4, 5, 6. The first item of these two vectors gives you a vector. And then the second item here is 10, and over here we have a nested structure. And this scalar pervades into it, so the 10 is used to multiply down into this tree structure. So we've got 10 times 7 is a 70, and 10 times 80 and 90 over there. And then there's an explicit each operator, which I guess you would call map. So I can do a plus reduce each, and that this isn't a scalar function, so it doesn't pervade. It's a function that works on, well, any rank array, but we can apply it explicitly to the items of an array with the each function. And this was very, very contentious. And Iverson left IBM in a huff. He hated the fact that this function here that catenated arrays together was invisible. He thought that was an abomination. And he headed off to IP Sharp and subsequently formed his own company, Iverson Software, where he implemented the J language and sort of implemented his rationalization ideas for APL at the time. And that's an APL that has a stricter regime of nested arrays. So in Sharp APL and J, you have to have homogeneous arrays. The primitive functions like plus, minus, times don't pervade. You have to use a box, an unbox and a rebox. So you would typically write plus under disclose if you wanted to apply plus to a vector of vectors containing numbers. And so the major vendors went off in two directions here. One, I think IBM had just put out DB2 and was very focused on tuples and the kind of data you would get out of an SQL query, whereas Iverson was still very much focusing on APL as a mathematical notation. And so there was this split. And then Iverson went off on his side and added some functional forms. As we point out, parallelizing individual SIMD instructions, a single plus or times, doesn't give you much speed up in real applications. You need more complex things. So we have operators, so reductions and eaches and so on. And Iverson was searching for more functional forms. He wanted to be able to express things like f plus g. So if you want to express in APL f plus g, how do you do that? And it took him 20 years. This is the case that took him 20 years. He couldn't figure out how to write f plus g until suddenly one day it dawned on him that he could just write f plus g, because that was a syntax error in current APL. You couldn't have a string of functions, f, g, h, without applying them to a right argument. So if you put parentheses around three functions, that gives you what is called a fork. So f plus h of omega is f of omega plus h of omega, which is equivalent to the mathematical definition of that. And the average using this, using forks, can be written as the sum divided by the count. So this is a points-free notation, where you can start creating more complex structures of functions leading into each other, which gives us more, as implementers wanting to parallelize things, it gives us more meat to more complex stuff that we can start to synthesize and parallelize. Right, so here's a dyadic one. So we could say, we saw this in the quadratic equation at the beginning. If we say 1 plus, comma, minus, that's 1 plus 0 and 1 minus 0.1 catenated together to give us a 2-element array. Okay. At the same time at Dyalog, a gentleman called John Scholes got very inspired by functional programming and decided that he wanted to augment the sort of very procedural, I don't know if you've seen any early 1970s or 80s APL, it's all full of branching expressions and hideousness that gave APL quite a bad name in those days. The code was really quite unreadable and horrible. So Scholes came up with, at Dyalog in those days, a functional form where a function is written with curly braces, and on each line of code you can refer to alpha and omega. Those are the left. Alpha is the left argument, omega is the right argument. A function can only have 1 or 2 arguments. You can have guards, so you say if omega is 0, then in this case return the first item of alpha. And del is a recursion, so that's self-reference. So this is a Fibonacci function saying, well, start with 0 and 1. If the right argument is 0, just return 0. Otherwise, take the left argument, catenate the sum of the left argument so far, drop the first element, and call it on omega minus 1. You can also use these lambdas, to write very trivial little functions, like in this case, left argument plus 2 times the right argument. A power operator was, so function power, you can say plus to the power 3, then that'll add the left argument 3 times to the right argument. The right operand of power can also be a function which is applied between the nth and the n minus 1th iteration to decide when to stop. So 1 plus the reciprocal of the right argument repeated returns the golden ratio. And of course this is parallelizable for selected operand functions. So if you use transitive closure where you're looking at you're combining rows on the left, columns on the right, and you're saying, is there any connection? You AND a row with a column, and then you say, do an OR reduction, do any of them connect? You can repeat that until you reach the fixed point. And of course, this is the kind of thing that you could split up into blocks and run the blocks in parallel and so on if you had a large array operand to apply it to. Okay, and then things started to get really modern and funky. The 1980s, Microsoft Windows, object orientation. We wanted to compete with Visual Basic, writing GUI applications. So the guys at Dyadic, this is long before my time, but I have to say today the design really holds up. So this says, make a form with the caption hello world using pixel coordinates and a size of 100 by 400. And you get something that looks like that. Nothing revolutionary about that other than that, this is just a quad. So one of the interesting things about APL is it cannot compete with the user in terms of names. You cannot have a conflict between a system name and a user-defined name. The system names are all either plus, minus, they're squiggles, or they are things preceded by a quad, which is illegal in the user-defined name. So you can instantly, when you're looking at code, see whether it's part of the base platform, if you like, or it's something the user has defined. And all you guys, being software engineers, are going to throw up your hands in horror and say, that means you can't redefine the system, right? I can't write my own version of plus to do quaternions or whatever. And that's true, it's in some ways a weakness of the notation, but you have to remember that this is a mathematical notation, and if it starts branching off in all sorts of directions, it ceases very quickly to be a means for communication between humans. It's clearly more powerful if you can read, plus is assigned minus and do all kinds of clever stuff. Anyway, moving on. This is about the parallel dot. So here's one of these lambda functions that goes from here to there. It takes as input omega, which is going to be 1, 2, or 3, and then it creates a button, with a caption of button and the character representation of the right argument at a position of 5 plus 50 times an array, which is 0, and the right argument. So if I run that, I get 3 buttons, nicely spaced. This is not a lecture about GUI design. So here's what I wanted to show you, is that I can then say f. So this is a reference to an object which is the form. And then within the context of f, there are these 3 objects called b1, b2, b3, which are the buttons. And then I can add another dot, and I can say caption and position. So this is the caption and position of the 3-element array of buttons within the form. So I get back a nested array, a 3-element vector with 2-element tuples containing the caption and the position of each of the buttons. So this is sort of off into the APL2 style nested arrays, but allowing arrays of objects. The important thing here is you can have arrays with objects in them, but arrays are not objects. So the array is a higher order of organization than the object. So you will never have array.shape, for example, to give you the shape of the container, because that's an array, and only the APL primitives apply to that. If there's a dot and a name, then it refers to each, it's mapped to each of the items of the array. Okay, so here I said, execute within the context of each one of those buttons, set the first element of the position to 50, and they all move down. Yeah, and it allows you to do things like, oops, I'll just throw all that up at once. Make a new OLE client, starting up excel.application, get hold of a workbook, extract all the sheets as an array. So this is a collection object, but this monadic squad, which is an indexing function, materializes a collection and turns it into a proper array. So it's a 3-element vector rather than being a collection object with methods and so on. And then I can ask for the names of my sheets, and I can say sheets.usedRange.value2 and get, for each one of my 3 sheets, I can get the full content of an Excel spreadsheet. No loops. Look, come on, no loops.
I have a nice question. When
Yeah.
you're showing these renderings of the data structures at the bottom, have you generated those manually in PowerPoint?
Right, okay,
or
that's-
is that come out of the system?
That's an option now in our session where you can turn boxing on. The traditional APL display would not draw these boxes.
Mm-hmm.
And typically that's not something you want in an application, but it's very useful when you're learning or
Yeah. Okay.
debugging, trying to find out how it all works.
Thanks.
Okay, and then I guess this is my contribution. This is work that this is after I joined Dyalog, and we were trying to find out a way to, because all these multiple cores were appearing, the CPUs had stopped getting faster, we needed to find a way to let everybody harness all the cores. And, when you've got a 30-year-old interpreter that was not written to be re-entrant, and, it's a rewrite and a 10-year bug curve, and since we make a living selling our software to people who use it, that wasn't an option, unfortunately. So we came up with this idea that we could have a special kind of object which we would call a remote namespace, where when you executed an expression inside it, it actually starts a separate instance of the interpreter and executes the expression in there. And then this is about the time also when we met Aaron and we were discussing these things, and that led to the idea that these could immediately return a future. So if you have one of these objects which is tagged as being what we now call an isolate, which is terminology that came from I don't know which programming language. Apparently this is mainstream terminology that we're adopting in APL now. If you make the kind of expression we had before and you dot into an isolate, you immediately get a future, and that's an array item that you can pass around, and if you ever try to use it for a computation, the interpreter just blocks. So here's an example. So I create We don't yet have these as primitives in the language. They're still written as APL models. So one day this isolate new will become a squiggle, but at the moment we write it as isolate new. So I say make isolate new each 3 empty arrays, which gives me 3 empty isolates. And I'm just going to, in each one of them, I'm going to execute quad DL4, which is delay 4 seconds. So I'm delaying 12 seconds here in a mere 4 seconds. That's pretty cool. The important thing is I put in a little function here that just displays the current time. So this was 7 a.m., 7:37 and 44 seconds. I executed this. I got back an array called delays, and then I asked for the time again, and you see no time has passed. Well, a few milliseconds have passed. And then I output the delays to the session, and that, of course, is a blocking operation, because to format the numbers, the interpreter needs to know the actual value of these results of the delay. So it waits, and then it gets back these. The result of delay in APL is the time actually waited. And now we can see 4 seconds passed. So there was an automatic block here because I needed to use the value of this array. So without writing any semaphores or any language construct, I just know that when I execute something here, I get a future, and it will block when I need it. And yes?
Is the whole array the future, or possibly its elements?
The individual items are individual futures.
Okay.
So if I had delayed 4, 8, and 12 seconds, and then I had displayed the first item, that would have blocked for 4 seconds. And if I displayed the whole array, it would have blocked for 12 seconds until the whole thing arrived. It also introduces the problem of first-class errors, because they can fail. So you can have an array which contains items which are actually errors. Yes?
Can you do futures that return arrays?
Can you
Have futures that return arrays?
Yes. Yeah, I mean, this one returned a scalar, but they could return anything. They could return something of any shape, and that's a problem that I hope I'll have time to talk about. There's a slide about that, because that's a nasty problem. Good question. We are also working on a parallel operator, which exists, but still in an APL model. So if you say F parallel, that's just another operator. Monadic operator takes any function. It creates an isolate on the fly, puts the function inside it, executes the function, returns a future immediately, and then when the isolate finishes doing its work, it's deleted. So say we wanted to count the co-primes below n for n equals 1 to 10. That's a pretty strange thing to want to do, but it's a nice short example. So I can compute co-primes by saying the sum where 1 equals the GCD of omega and all the numbers up to omega. Yep. So if you take all the numbers up to omega and compute the GCD with omega, then if the result is 1, then they are co-prime. So for the numbers up to 10, 1, 1, 2, 2, 4, etc. That's not the point. The point is that if I think, so this is a mathematical statement, right? But if as an APL programmer I think, there's no side effects, I think that's worth running in parallel, then all you need to do is to throw in that symbol, and the APL interpreter will then actually run them in parallel. So you're leaving it to the user to decide, yes, but our experience, this is something to give people bang for the buck right here, right now, and the user does generally know whether going parallel is a good idea. So futures can be passed as arguments to other APL functions without blocking. The interpreter will block automatically if it encounters a primitive function which actually needs to know the value. And that means you can chain parallel calls. So I fire up this thing and I say I want to compute the number of coprimes for the numbers up to 100 in parallel. I immediately get back a 100-element vector. I can ask how big it is and get back 100. There's no blocking, because that's just the shape. It doesn't touch the content. I can even do, this is a partitioned enclose, where I'm partitioning, make the 100 reshape of something which has a 1 followed by 24 zeros. So I'm cutting this 100-element array up into 4 chunks of 25 each, I'm still not touching the content. So I now have a 4-element vector called quarters. I can ask for the tally each, the length of each item, and be told there's 25 in each. And then I can say, well, compute the average using this fork, parallel each quarters. So that's going to launch now another 4 potentially isolates, which now do need the value. So they are each going to block on their group of 25 items. And then they're going to be released as soon as their set of 25 number is released. So I mean, in this case, probably the interpreter will execute this expression faster without the parallel eaches, of course, because there's TCP communication going on and all kinds of stuff. But this is just for illustration. There are people who are using this very successfully on, quad 8 core machines. Yeah, Brian.
So you carefully use the term potentially for, what's the fine print there? You said it would launch potentially 4 tasks to do the 4 quarters. If I heard.
Oh no. This is 4 because
okay.
There are 4 here.
Right.
So this is a parallel each. That's definitely 4.
Okay. Right.
Yeah.
Thanks.
So we used 105 threads here to do this, and yeah, we're putting it in the hands of the user. But the important thing in the design of this, from our perspective, since we're designing a mathematical notation, is that you can insert those parallels and you can take them out. And as long as the things you're dealing with are pure functions that don't have side effects, you're not changing the math at all. So somebody who's looking at this as a mathematical statement can ignore the parallels. It's completely deterministic as long as those are proper functions. And of course, if you're writing a real application, they can have side effects and then you're on your own. But that's how things were already. Right, so there was this split. So that's our asynchronous story. Like I think Brad said, this is being used by people, so we have to do all the dirty stuff as well as the nice and pure stuff. But here's an interesting thing. So there was this departure in 1982, 3, 4, depending on when the various vendors did their stuff. And now that we're funding all this research, we're getting in touch with the guys who did the original work. We have Roger Huey, who worked with Iverson and on J. He's now working more or less full-time for us, and we've been bringing a lot of the Sharp APL stuff into Dyalog APL. And I think this is actually very significant from a parallelism point of view, and hopefully I'll have time to show you why. So we're actually starting to integrate these Sharp APL operators into an APL2 language core, and they have a different flavor. They favor homogeneous rectangular structures, and they emphasize the leading rather than the trailing dimension. So quickly get through a couple of the most important ones. So the rank conjunction, this is perhaps the most significant one of them all. So we're doing a multiplication, and we're saying we have a left rank of 1 and a right rank of 0. So that means we're going to take vectors on the left, scalars on the right, and do multiplication. So we're multiplying those by 10, and then the second row, we're taking another scalar from the right and a vector from the left. So it's sort of like each left, each right, and so on, but with much finer grained control. Yeah. You can specify exactly how you want to fetch items from the right and left. Rank operator. So we have here's a 3-dimensional array, 2 planes, each one 2 by 4. If we just say we want to average that, so the plus reduction along the leading dimension divided by the count, that goes through the planes because the planes are the leading dimension. But we can say compute the average rank 2. What that then does is it applies the average to rank 2 subarrays. So it's doing a plane at a time going along the leading dimension of that. So it's now computing the average of each column. And then finally we could say do the average rank 1, in which case we're applying the average to the rank 1 subarrays and averaging the rows. So with our average function we can compute the average along all 3 dimensions simply by using the rank operator in slightly different ways. The key operator is is very closely related to that, except there you're not dealing with sort of positional indexing, but you have two arrays where one of them represents some keys and the other some values. So key is an operator which takes a left operand function, which it applies it applies once for each distinct key, so it's going to apply it for red and for blue. And it's going to pass it as the argument, the key value, and all the data values corresponding to that key. So if we just use this almost no-op function, which just returns the left and right argument as a tuple, we get red and the values corresponding to red. And if we said, well, we want the keys and the tally of the values, then we're counting, this is a frequency count, a histogram of the values. Right, so there's one operator left. Well, there's several operators left in sharp APL and J. We think this one is really the next one we want to steal, and it's very relevant, I think, to almost all the presentations that have been in this room so far today. It's the cut. So the cut is something that allows you to do tessellations or cut subarrays out of an argument. So our right argument here is a 5-element vector, and we want to do cuts of size 3 with the identity function, just to show you what shards we get out of that. And then there's a variant. This is a little bit nasty, but we don't have a better idea right now. We're still designing this, so I don't have a legal department, but it might not look anything like this, but it will be similar to this. So this says, don't give me any shards that are smaller than a full shard, the -3. So I get 1, 2, 3, 2, 3, 4, and 3, 4, 5 out. And then I can also say, well, I want stride of 2 and window size of 3, and get something like that. And then, of course, the operand function could be plus reduce or anything that you like. It doesn't have to be. So here's a slide we've seen before today. I wanted to see what people were going to be talking about here today, and I found your presentation online. It's probably a much older version of the presentation. And I thought, well, how would we do this in APL? And there's this slide with the code on it. And I thought, well, how would I write this in APL? And obviously in APL you want to use a global view because you're the domain expert and you don't want to be worried with what happens at the edges. So you could say, for example, average the 2 drop of A plus the -2 drop of A. Right? That's a very direct way to express. This is the -2 drop and this is the 2 drop, and average them. Or if you have cut, you can say, well, I have a stencil which is 0.50 and 0.5. I'm not interested in the middle bit. Do a dot product. Use a dot product with that stencil as the function and apply it to length 3 arrays. Right? And then, of course, we went to higher dimensions. So there's this. You saw this in Brad's opening. I think it's almost this exact slide. So in APL, the way this would work out, I think, is you'd say, well, okay, there's this funny constant vector. I don't know what that is, 0.5, 0.25. So I'll just type that in. Index it by the outer product of 101, null dot plus 101, null dot plus 101. Turns out to compute the weighting that you want. And then it's because these are 3-dimensional, we can't use the dot product because that would be combining rows and so on. So we just have to get our 3-dimensional cut. We need a 3 by 3 window, multiply it by our 3 by 3 array, which is the weights, ravel it, and do a plus reduction. Yeah. But then, of course, when you're an APL programmer, you look at that and you think, it's got to be rank invariant, right? Good APL code is type, shape, and rank invariant. So this was absolutely not satisfactory. So I was sitting in my little RV that I've been sitting in for the last couple of days preparing for this, and I was exchanging emails with Roger Huey and looking at this code and saying, well, how would we do it? Okay, so, for you, I will set quad IO to 0. I'm going to copy the model of cut that we currently have. I have an array which is, and this is really to show you, this is not invented, and this is how we actually work interactively. Okay, so there's a 6 by 6 by 6. array of some not very likely numbers. I can execute that. What does it look like? It looks like that. Yeah, well, but, okay, so I can compute it. And there's my S0, which is the result of applying the stencil. What's the first item? It's 172. The 333 take of R is that. So that's the top left cube. Apply this computation. Yeah, that is 172. It all looks right. And then you look at that constant and you say, well, what's that? So apply the window division. Ah, those are actually all factors of 2, smaller than each other, right? So let's see. So if I start by computing the rank of my array, and then I take 0.5 and raise it to the power 1 plus iota rank plus 1, then I get those constants in a rank invariant way. And this thing here, which is that selecting which one of those you want to use, if I want to do that in a rank invariant way, I can start by taking the rank reshape of enclosed 101. And then, of course, I can apply the outer product plus reduction of that. I have to disclose it. It ends up being enclosed, but that's a minor point. So I can write that. Instead of doing that, I can write that. So now I have a rank invariant expression. And if I try it with those weights and I match my original convolution result with a new one, I can see that I'm on the right track. And I look at this thing and I think about it a little bit more, and I'm discussing with Roger Huey, and he said, but hang on, we don't need to do that indexing, because that's actually 0.5 raised to the power of those numbers, right? We don't need to create an index vector and index into it. We can simply raise 0.5 to the power of that matrix 0, 1, 2, 3. So we end up finally then with some weights, without indexing. And then it struck me, well, do we really want the sum of the weights to be 4? Or maybe we should be normalizing them, divide the weights by the sum of the weights and turn it into so that the sum of the weights is 1, so that you don't change the range of the data. I don't know whether that was the intention with that code, whether that was actually a bug in the code or what. Anyway, with 2 minutes to go and a number of slides left. Okay, so we've seen that. Move on. Another hot application that we have people looking at the moment is like neural networks. They really, this is an expression which explains how sigmoid neurons work, if you know anything about that. Reciprocal of 1 plus e to the power of minus, and then a dot product of the weights that the neurons have been programmed with and the input stimuli that you have. And of course, it's easy to see how you would you guys could optimize this easily with your array of tools that you have at your disposal. But the important thing is that not only can you easily optimize it, this mathematical expression is actually useful for teaching how neural networks work. It expresses mathematically, very directly, what a neural network is doing. There's a couple of points worth making here. That departure ended up with these 2 sets of operators that really have quite different flavors. The APL2 and therefore the dialog-based ones encourage the use of nested arrays. So if you wanted to apply the function foo to the rows of a matrix, you would split it into a list of vectors, apply foo with each, and then mix it. And as we saw with the isolates, when you apply a function foo inside an isolate, you get a nested array back. Whereas the sharp and j forms use like the rank operator, which applies the function to the rows and leaves you with an array result which is still a dense. If foo also returned a vector, you still have a dense array. So the APL2 is driving towards arrays of tuples, and sharp APL towards tuples of dense arrays, which is also a topic we've heard discussed here earlier, where I think the highly parallel code does much better if you have tuples of dense arrays rather than arrays of tuples. And people are doing clever things to unfold that. So this is perhaps, maybe I'll do one more slide after this one. So, you know, why bother with APL? Why do you need these things? You've got BLAS and LAPACK. And the point is, I think, that this small collection of very general operators really promotes array thinking. Once you get into thinking of using these tools to describe array algorithms, it changes the way that you think. It really is a tool of thought. And of course, under the covers, an interpreter or a compiler could be calling BLAS. And you can combine things like we saw, you know, here's not a very complicated function that we're applying with a stencil, or a transitive closure, power, limit. These are things that are very useful from the mathematical point of view in describing what's happening, but also I think I call them soft optimization targets. I think, you know, many people here know exactly how to do that. And maybe we'll stop with this one, because I think this is a very interesting discussion. You know, how do you optimize something like key with alpha and tally omega? So you give it an array of only keys in this case. I didn't provide it with any data. It generates some data which is just the index position of each key. So I'm just counting, you know, there were 4 1s, there were 5 2s, and there were 2 3s. And I think there are different schools of thought here. I think at least Aaron can argue with me about this. Since he's here, he would say avoid primitive libraries, use standard libraries, and use all the standard compiler tricks to inline them and so on. Whereas others of us would say, hey, but you know, you can recognize this at a very high level in your AST and say, well, that means it's a histogram, just compute it. Yeah. So, yeah. Rather than perhaps spending some of our best minds writing compilers that try and detect parallelizable loops in scalar code, why not use a high-level language that allows you to express the parallelism directly and then try to efficiently exploit the parallelism which is apparent in the code, which is a hard enough problem. You know, there's still lots of PhD subjects to pick from. And there are some people, I mean, Bernecki and Schultz, who were here, had a paper here last year, and Aaron, whose time I'm stealing now, has shown, you know, have shown very interesting progress in the direction of computing that. Yeah. Sorry, I took 3 minutes of your time and left no time for questions, but I'll be here in the break.
Well, thanks.
Yeah. Thanks.